So, welcome back on chapter number 14, Chemical Kinetics. In this video, we will study about the reaction rate, how we can write the reaction rate. So, reaction can be fast and slow. So, here are the thing that why are some reactions are violent and some slow. For an example, decomposition or explosion of trinitrotoluene is within a second, and diamond to graphite is takes million year, right? So we have seen this why some reactions are very slow, some reactions are fast. We have seen the four factors that affect the reaction rate, which and based on that some reactions are fast, some reactions are slow. You can review the previous video. In this video we are going to write expression of reaction rate. So what is the meaning of expression of reaction rate? For an example, if you are traveling from distance x1 to distance x2, this is your home, you are going from here to this place, so I will call this as a x2 and this is your x1. You started in time t1 and you reach in time t2. So rate is the change per unit time. Rate of speed is equal to change in position divided by change in time, right? So what we can do, we can subtract how much distance you cover from x1 to x2. So x2 minus x1 divided by t2 minus t1 will be the time change in time and change in position. So we can write like delta x divided by delta t. So delta means difference. This sign, the triangle sign, is called delta, right? And delta means a change. How much change occur in the distance, how much change occur in the time. Same way, when we talk about any chemical reaction, A to B, A is my reactant, is converting into product B. When we write the rate of reaction, we write the change in concentration divided by change in time. So here we can write like a B2 minus B1. So initial concentration was B1, and final after T2, after time T2, concentration become B2. So delta B over delta T, change in concentration of B means product divided by change in concentration of time. So here big bracket shows the concentration, and if both the reactions are occurring in the water or in the some liquid phase, so units usually for the liquid phase is molarity per second. So this is the unit for the reaction rate, molarity per second. So here like a molarity per second, or if we are talking about molarity per hour, molarity per this time could be anything, but at the end you can convert molarity per second. Next is we'll take one example. So for an example, if methanol CH3OH in water, aqueous means water, is reacting with HCl, this is also in water means acid. So if hydrochloric acid is reacting with methanol, it is converting in methyl chloride plus water. So these are the two reactants and these are the products. So what happened to the concentration of the reactant and product as the reaction proceed? So as the reaction proceed, the concentration of methanol and hydrochloric acid decreases, and the concentration of methyl chloride and water increases. So the concentration of reactant, we can also say that concentration of reactant concentration, basically reactant concentration decreases because they are going to be consumed, and product concentration increases slowly. As reaction will proceed, you will get more and more product. So the reaction rate is defined as the change in concentration per unit time. So this is again the same definition which we have seen in the previous slide. How we write the reaction rate? expression of reaction rate, the same reaction we are taking. This is the basic formula. Rate means change in concentration divided by change in time. So for an example, if we have to write the how much change occur in the methanol in the reaction, so we will write like this one: delta in big bracket methanol divided by delta T. So bracket represent the concentration in molarity and delta indicate the change. So we have to write how much molarity changes from certain time to certain time in and divided by delta T. So this is the basic expression, change in molarity divided by time. Let's talk about one more thing here, that as we know, suppose you have 1 mole initial concentration, and after, suppose you have 1 mole concentration at T1 time, and after T2 time this become 0.7 mole, right? So basically if you will subtract, right, like 0.7 minus 1 and T2 minus T1, so answer you will get basically minus 0.3 divided by 0 delta T, right? So usually we represent, and also okay, one more thing, here we have a bracket and we write for reactants we usually put negative sign in front of the rate. So what will happen, let's open the negative sign now. So here is the negative sign and outside is also negative sign. Once you will write at the end, you will get basically 0.3 divided by delta T. So rate will you will get in positive, but for reactant the negative sign indicate the rate of disappearance. It means this negative sign is showing that this is the reactant and it will disappear, right? So we can summarize and we can write the reaction rate for each of the reactant and product. Delta change in molarity of methanol delta T, delta concentration change in hydrochloric acid by delta T. In case of methyl chloride, same thing, delta in big bracket methyl chloride divided by delta T, and delta in big bracket water by delta T. In case of reactant, we will put the negative sign because this shows that reactant will disappear, reactant will consume, and in front of product we write the positive sign that shows it is producing, concentration of product will increase. Usually we do not write any positive sign, it means there is a positive sign, right? So let's take same example in the form of question, how to calculate the rate of. So the rate of disappearance of H plus ion was measured for the following reaction and the following data were collected. So time in the minute and hydrogen ion concentration in molarity is given. Calculate the average rate of the reaction for the time interval between each measurement. So here you can see methanol is reacting with HCl and it is producing methyl chloride and water. And why they are giving me H concentration ion? Because HCl, when it goes into water, basically it produces hydrogen ion plus chloride ion, and hydrogen ion concentration you can calculate through the pH, right? Through pH measurement you can measure the pH at 0 minute, 79 minute, 158 minute, 316 minute, 632 minute, and once you know the pH, you can back calculate how much hydrogen ion concentration will be there at these time with those pH. So these are the concentration which are given hydrogen ion concentration. It means hydrogen ion concentration, if you will see, basically it is decreasing. So HCl is disappearing slowly, right? Now we have to calculate the rate of reaction between each time. So here we have, I have already calculated, so we'll go with this slide first. So what we will do, we can take these two first. So 185 molarity to 167, then 167 to 1.67, and then 1.67 to 1.52, 1.52 to 1.30, and then 1.3 to 10. So how we will calculate the rate of disappearance? So rate of disappearance of hydrogen ion concentration, we can write the expression like this one: negative delta rate change in molarity of hydrogen ion concentration divided by delta T. So rate of disappearance in the first condition, you can see this is molarity 2, 1.67, and initial molarity was 1.85. So we have to calculate final molarity, initial molarity. So 1.67 minus 1.85 molarity divided by T2, this is T2, this is T1. T2 minus T1 means 79 minute minus 0. And once you will calculate, you will get the answer in the parenthesis negative, but once you will open the parenthesis, the negative sign will change into positive. So basically negative sign is showing that this is a reactant and it is disappearing, but the rate will come in the some positive value. So rate, once you will calculate, once you subtract and divide by 79, you will get 2.3 times 10 to the minus 3 molarity per minute. I am not converting here into seconds, but just leaving as such, molarity per minute. Same way we can calculate the rate for condition number 2, 3 and 4. So for the condition number 2, which is 1.67 and 1.52. So here in case of condition number 2, the molarity, final molarity I am using this like 1.52, and initial I will consider this 1.67, because we are calculating from 79 minute to 158 minute. So molarity final minus initial molarity, final time, initial time, subtract, do math, and then calculate the rate. So 1.9 times 10 to the minus 3 molar per minute. In the same way, once you will calculate the third, you will get 1.4 times 10 to the minus 3 molarity per minute, and fourth one is will be here. So if you will see the trend, basically if you will see the trend, initial rate was 2.3 times 10 to the minus 3, then 1.9, then decreases to 1.9 times 10 to the minus 3, then again decreases 1.4 times 10 to the minus 3, then again decreases 9.5 times 10 to the minus 4. So as the reaction proceed, rate of reactant decreases, right? So as the reaction is proceeding, as the methanol is reacting with the HCl, reaction rate becomes slow and slow and slow and slow, right? So rate decreases as the reaction proceed. So here we can summarize this concept in the form of graph also. So reaction rate for the following graph: how does the concentration of the reactant changes with time, and how do the concentration of the product changes with time? How do these changes relate to each other? So we'll see this change reaction occurring and how they are affecting, how we can read the in the form of graph. So here is another example is given where dinite N2O5 is converting into NO2 and oxygen O2. So here this is the reactant, NO2 is product, O2 is product. If you see the graph, y-axis is plotted with the concentration molarity, x-axis has a time, from left to right is increasing, concentration is increasing from bottom to up. So if you see the first, this green line, which is for NO2, so this shows the react product is increasing over the time, and oxygen is another product, which is the red line. This curve also shows that the product concentration is increasing, and the blue line which relate to N2O5, so this decreases the concentration. So rate of the reaction is decreasing over the time, and that we have seen in the previous slide also, that as you will proceed the reaction, your reaction rate will become slow and slow and slow. The same thing you can express in the form of graph, and if you want to calculate the rate at these 2 points for the reactant, basically you can find out, you can draw a straight line from here to here. This is your initial concentration, and from here to here this is your final concentration. So what will be the change in molarity? This will be like 0.0019 molarity, and time will be from these 2 points will be 300, 400 minus 300 means 100 seconds. This is second. So this divided by this, you can get the rate. So you can get the rate at each point, and you can see the graph is reducing. It means it is showing the molarity of the reactant is decreasing over the time, and these two graphs shows the molarity of product is increasing over the time. So we can write one thing here, that reaction rate and stoichiometry. So in the next video we will study about the reaction rate and stoichiometry, how stoichiometry is affect on the reaction rate in the expression.